speak on atomic filamentations and conductance quantizations in HBN and HFO2 bilayer resistive switching devices. And it's talk for half an hour. Huh?
Yeah.
So, please go ahead.
Thank you, and I'd like to thank the organizer for inviting me here. So initially my talk was placed in the wrong topic, so that's why finally they have rescheduled thing here. So anyway, what actually I'm going to show that recently we published some interesting thing what we're doing with the bilayer structure like a HBN and the hafnium oxide. Both are dielectric material. One is 2D, one is the 3D material. So 2D 3D combination. So what actually I'm going to show here the atomic filamentation, because how this actually controls your quantum quantization. So that conducting path actually how it is forming. So that I have to discuss in this topic. So first just gives a kind of glimpse of where actually you are located. So this is Srinagar University. So this is in the airport. So you can take directly to the Parichok, and there is a ring road, and it's called EPE. So you can go to directly to the campus. So here recently the new airport opens. This is called Jiwari Airport. So I think already you get the information. And this is the aerial view of the campus. So it's a 385-acre campus. So it's a library, and this is the academic blocks. So you have our residential apartments inside, and also administrative block also inside. So now directly go to the topic. So since the time is very less, so first I give brief about the memristor. How does it work? So basically, memristor, there are 4 different kinds. So it depends on the material. Either it's a ferrotic material or magnetic material, phase material, or the resistive random access material. So here actually in my case, actually I am talking about the resistive random access material. It's called RAM. So it's a very attractive at this moment because of the different possibilities like a non-volatile memory, logic gates, and the synaptic device for neuromorphic application. So since the topic is not going to that direction, so I am not going in that details. I just briefly tell that what actually it's, how does it work. So it has just like a capacitor. You can see that dielectric material inside. So this is called switching material where the resistance changes, and we have 2 different electrodes, top electrodes and bottom electrodes. And this interface and the material both play a very nice role in controlling the resistive switching properties. So among different models we have in literature, so there are 2 different models. Those are very popular. One is called the cation based, one is called the anion based. So generally, if your material is active, so then in that case, what will happen when the potential actually have been given between the 2 different electrodes, then the cations they move inside and they make a filament, and that's called the set. That means that it becomes conducting state form through which the current actually flows. And when your potential reversed, then this some of the cation will return back, and then remaining kind of insulating. So because it's a metal oxides, so that's why insulating property is there. So it becomes resistive. So in one case it will be conducting, other side it will be insulating. Similarly, in case of the non-interactive material, so non-reactive material, both sides, top electrode, bottom electrode, in that case, if the conducting filaments actually form, it is happening because of the is called the oxygen anion actually is travel through the your insulating material and make the your vacancy channel and make the conducting filaments, and it grows with if potential is increasing, then it grows with time. So then it becomes very strong. Okay, so generally we put some kind of compliance so that it should not destroy your SMU source measuring system unit. Whenever you reverse it, then this oxygen return back to your metal oxide system and then become the insulator. So these 2 mechanisms are actually very well known in the literature. So one is called the electrochemical metallization, ECM, other is called valence charge memories, that's called that VCM. So one case is oxygen vacancy, other case is the cation. So you should keeping this mind. So my topic will go inside. So how the quantum conductance is actually coming into picture. So since I said that, so this is the thing actually I wrote for your remember. So that takeaway message, the resistive switching actually is happening because of the formation and rupture of the conducting filaments. This is called the filaments. Okay. Now Next thing is that, so when things actually happened, how do I know that it's really happening? So this mechanism, when it happens with the cation part and the anion part, so generally the IV look like this. So if we sweep the potential from plus to minus and minus to plus, then for cation cases actually it generally take this kind of shape. And since we put the compliance to avoid any kind of destruction in the your source measuring unit, then you just cut the current measurement up to this was the compliance, and then you can return back. When you reverse the potential, it will be passing through your origin. Okay, so this kind of shape actually it takes. By looking, you can tell that it is the cation driven. But if it is not like that, if it's happening like this way, so it is like a gradual increase and then there is a depression and then coming back. So this actually kind of a feature of oxygen vacancy related transition. So what actually happened in this case actually, so some kind of virtual filaments actually form inside the oxide layer, and that actually controls the gap between the two different electrodes. And when it is matured, that is the final state will appear, then the system becomes stable. Okay. So the main issue in this kind of system is that it start acting after giving a certain potential. So people are really searching for some material where you do not have to create the oxygen vacancy by giving high potential. Okay. So so that means that you can save the high power application. Now the question is that since I will talk about the conducting filaments formation, so if the conducting filaments now become the atomic dimension, that means that you are shrinking the dimension of the filament width, then what will happen? It's called the nano conducting filaments actually form. Then you can see the quantum conductance mechanism. So generally this kind of phenomena actually have been discussed by Landau formula. So this is the formula you can see over here. So where alpha actually this is a kind of the shape parameter, the how the conducting filaments end will look like. Okay, like here actually kind of projection we are showing. So you can see the two edges. So at the end actually it is atomic dimension. So here is the potential barrier formed, and this is the gap. Okay, so the potential gap through which the electron will travel. So that means the transmission probability actually ultimately control the how the current will flow through this. So now if the alpha, because whenever you are sinking down to atomic level, so you can tell that this alpha tends to 0 if it is very small enough, then this I, the current is proportional to the G naught. So you can reduce down to, so this G naught actually nothing but the 2 E square by H, which is coming around 77.5 microsiemens. So this is the unit actually called as the quantum conductance unit. That is the minimum dimension, actually minimum value actually you can get whenever you are coming to the atomic level. So by knowing that, actually we now think about how to prove that this really actually happening. So here actually we have chosen two different materials by keeping this in mind: low leakage current, okay, then the high thermal stability, then high breakdown field, and the large on-off ratio. These are four different components actually we have to think about before choosing. Then we found that the hafnium oxide and the HBN, they have this kind of property, and also they are very matured in literature. So you can see that hafnium oxide, so they are CMOS compatible, robust oxygen vacancies there. So you can find oxygen vacancy driven conducting filament formation. Then atomically thin layer can be formed by HBN, and it impairs the sneak current. That means that you can in the reset part actually, in the off state actually, it can minimize the loss of the crosstalk between the different arrays. So to know this, now how to prepare device? So what we do, we take some electrode. Here in this case we consider the ITO, and then we grow hafnium oxide by using 2-inch hafnium oxide target by RS magnetosputtering, and here we use the 80 watt 30-minute deposition actually, and 3 millitorr pressure we can maintain in the chamber, and in this way we grow around 20 nanometer thick hafnium oxide. Then on top of this we make the electrode by shadow masking. This is called silver electrode, and finally in cross sectional view like this, so you have the top contact, and finally we can measure like that. Okay, so whenever we are giving the potential, we just you just change the applied bias and take the voltage sweep and measure the current. And whenever we have this HBN into account, then what will happen? Actually, we just dropcast the exfoliated HBN layer or flakes, which is dissolved in IPA, and then we just dry it up by heating at 100 degrees centigrade, and then we just some kind of flakes will form on top of this, and then we make the electrode. The same way actually we did on the hafnium oxide layer, and try to see that how does it work, because hafnium oxide is very HBN is a very dielectric material and it should not allow, because no oxygen vacancy can penetrate through. So what will happen in that case? So in the beginning, before testing that one, actually we just want to see that whether hafnium oxide really working well, as like the way the early literature actually people have been discussing. Okay, so we have taken the IV characteristics. You can see that it's a butterfly kind of structure actually coming, and this was a set and reset, set and reset, which confirms that the hafnium oxide layer actually performs very nicely, and it is very stable also. You can see that we have gone for 1000 sweep in DC sweep, but still there is no change in the loop. So that means that this sample actually very stable, and we also analyze deeply, and you can see that it has the conducting state, and you have some kind of your SCLC region. So we measure every details about this, so we are not going details about that. Then we also check that whether if I give the reset potential, if I change the reset potential, whether can I increase the loop significantly. So you can see that up to 3 volt, 0.5 volt to 3 volt, it gradually increases the loop dimension. Okay, that means that it can store a lot of, and we can make a lot of different states. So at least 5 different states actually, or 5 different states can be observed in the your HRS state, and also it's very stable. You can see there is no much difference in the your cumulative frequency. Cumulative frequency whenever you are going to the your HRS actually changing from 0.5 volt to the 3 volt. So that confirms that the device actually perfectly working. Then also we check the compliance current dependency, because these are 2 different tests actually people has to make to confirm that your device actually really works well for future application. So then we did it, and also here in this case what we did in the set potential, set value, what we did, we changed the current, compliance current from 10 milliampere to 30 milliampere. So you can see that slowly you can go to the 6 different steps. That means that we can get 6 different states, at least 6 different states by giving the DC potential. Okay, and this state, number of states actually, if we have more number of states, that means the more state means more occupancy of the electrons, and so you can utilize for the some computation in future. So since in this case we are changing the compliance current, so here the LRS will be changing because current increases. So that's why we have the states changing in the LRS part, not in the HRS part. In the previous slide actually we are talking about the HRS part, when the potential has been changed. Okay, so also he shows that very systematic way of increment, so no not much difference in the tendency of this current whenever changing the potential. So to confirm that it's really happening and in the nanoscale level, so we also did the CFM study. So what you can see over here, this is the HRS part where the sample have been given the plus 10 volt. So you can see that the current is very low, but in the middle of this, if I reverse potential actually is given, that is minus 10 volt has been given, you can see the current is really high. Okay, so we can just make a trace across this, and you can see the LRS state actually having more current than the HRS state. So that confirms that even it is not only the only one point, you can find the distribution of the HRS and LRS all over the surface. And how this is working, so then we magnify it, and whenever we are putting in the 3D mode, then you can see that this kind of spikes are formed. These spikes are nothing but the current, from where the current actually coming up, and not everywhere you can see like this. Some regions actually it is having like that, and that confirms that this is the region where the conducting filaments actually formed. And if you keep on doing this, then what happens, sometimes actually found that gradually these filaments start mingling together and then make a channel. Okay, so then we have just given the model, and we also published in Advanced Material Technologies recently. So where actually we showed that by giving the potential increase or the complexity increase, 2 different models. One case the conducting filaments actually is increasing dimension. Other case actually your gap between the your insulating gap is decreasing because of the different potential. Now coming back to the when the HBN actually dropped on this on top of this. So now in the beginning actually we check the your hafnium oxide crystallinity. So it's a kind of mix of the orthorhombic and the your monoclinic phases. Then we put the HBN. This is HBN hafnium oxide bilayer structure, and it is a pure HBN on top of it. What you can see that this particular peak actually coming from the your HBN, which standardized that your HBN is actually in the better form. Okay, so we magnify this part, and we have seen that both monoclinic and the orthorhombic phase actually exist in the hafnium oxide layer, and some TiO2 layer actually crystallizes. So some peaks coming from the substrate, and this is coming from the HBN. Then we perform the XRR, and this XRR actually tells us, that whenever we feed the data, what we found that the approximate thickness is coming about the 16 nanometer of hafnium oxide, and here the scattering length density increases towards the surface. So whenever you feed the data, you can find that your SLD actually increases, and that signifies that your oxygen vacancy actually going to be increasing towards the surface. Further, we did the Raman study of the same sample. What you can see that whenever we put this HBN on hafnium oxide, there is a shift, and that shift actually confirms that there is a strain. And this strain also observed in case of XRD. You can see that this peak, HBN 002 peak, actually has been shifted whenever you have grown on top of the hafnium oxide layer. So that means that some strain actually develops by growing onto the hafnium oxide layer. Now this is the device actually we formed. So as I showed already previously, then we put the your masking, shadow masking, and put the silver. This is the silver electrode, and there is this scattered thing. Actually, it is the HBN flakes. Okay, and below this actually you have the hafnium oxide layer. So this is a cross-sectional view. This is a hafnium oxide layer, and this is a HBN layer. Okay, and now if I magnify one of the silver dot, then this looks like this. So it's annular geometry because since the thickness is not so too much, so that means some of the part actually still remain vacant. So the thickness of the silver is not so high. So that's why it does not change the contrast. But by doing this EDAX scan, actually we confirm that we have the silver on the surface, and then also we have the HBN. You can see the boron, you can see the nitrogen, and also you have the oxygen and the your hafnium. And since we are having this your ITO on the one side, so since your spot is really big, so that's why some ITO signal also coming, indium, tin, and oxygen signal also coming in. Okay, so after confirming that, actually we perform the IV characteristics like the same way I did for the hafnium oxide layer. So now what you can see that here actually it is not like as the way we have seen earlier. So here you have the step-like structure. Okay, and these steps actually very interesting and very regular. So if I magnify, if I make the zone 1 and region 1 and region 2, if I magnify it, you can see that the steps actually it maintains some kind of, because G naught, I already said that 2 is squared by H, which is called the quantum conductance unit. So it is a kind of multiplication of some factors. Okay, so it maintains something like that. So whatever time actually you grow, so it is coming. So to understand the why it is actually happening, so this conductance actually happening. So like I said that earlier in the beginning, that whenever you reach to the atomic level, so then in that case what will happen, because your I is proportional to G naught V, so that actually the quantum quantizes the conducting path. So for checking that this really this theory actually what is known actually is really feasible or not. For doing this, actually we go for the CFM once again. This is first actually check the topography. So we find out one of the HBN flake, relatively smooth part, and then we perform the CFM. And what you can see here, this part actually is a light, and this is a little dark part. That means the current is more near the edge, but in the middle of this HBN layer, very few current. Your current is very poor actually. And then if you plot in 3D, then you can see the some kind of spike, that whatever we have seen in case of the hafnium oxide layer. So where we found the conducting flex form, your conducting filament formation. But this filament, instead of forming inside the layer, it formed at the boundary. So that means that the oxygen vacancy which is reaching up to the surface, they make a contact to the top electrode by the edges. So that means the electrons actually going through the edge of this hafnium oxide layer. And if we take the trace of this inside this plane, okay, where the current is low, what you can see that it's a off state to the on state. So the ratio of the current is very, very low. That means that it's already proved that the current through the oxide, your hafnium oxide HBN layer is very poor. So mostly they are reaching near the interface levels. Based on this, and also performing your time dependent pulse potentiation, what you can see that stepwise increase of this conducting state whenever you do the AC measurement, okay. And here in DC, also you can see that if I increase the potential from 0.8 to minus 0.8 to plus 0.8 volt and increase to 0.9 to plus 0.9 volt, you can see that the number of steps also increasing. So that means that if you give more potential in DC, then more such path, a sneak path will be forming at the boundary level, and through this actually our understanding actually we make this kind of model. Actually we are giving a model which says that at low potential actually the HBN layer kind of is blocked and the current, the vacancy reach up to here and then reach to the conducting your silver layer, the conductance coming through the edge of this hafnium oxide HBN flakes. And if we increase the potential, then more such conducting filaments will be forming and more such steps will be forming. Okay, so this actually says that atomic scale filament restructuring by increasing potential, and this one actually shows that the evolution of the quantized conductance states by which is mimicking the biological integrate and fire synaptic learning. So this is the way actually people check that whether it will be really applicable for the pneumomorphic application for future application. So with this actually I conclude because I am on time. So here actually I showed that engineered oxygen vacancy driven conductive filament formation in hafnium oxide layer from membrane application. Secondly, I demonstrated the defect control multi-level resistive switching behavior in reset when the potential has been changed and the set processes when your compliance current has been changed. And thirdly, actually I showed I revealed the nanoscale filament localization and quantum conductance states at the edges of this HBN flakes in the HBN hafnium oxide heterostructures. So this work actually is a PhD thesis work of one of my students who is submitting this month, Tanmay Tarija, and also the financial support from my university, Shivnath University, and your ACRB. That time it's still this financial support for performing these experiments. Thank you for your attention.
So now session is open for questions. Yeah, that is it.
Yes.
Thank you very much for the nice presentation. I have one question regarding the discrete conductance contraction steps. So first of all, do you always see it as a 1 G0 difference in the plateaus?
You see that I said that whenever you have only one atomic dimension, then only you can expect I naught equal to the G naught V. But whenever you have a flake, you have multiple such atoms sitting at the boundary.
It's a parallel combination.
Yes, so that's why you are getting some fraction. Actually, it's not the integer of some.
This is one reason can be possible. Another reason can be that when we talk about the atomic conductances of gold, it is 1 G0. But atomic conductance of platinum, example, is 1.5 G0. So it is possible that atomic conductance, because of the HBN or the hafnium oxide, their combination is not 1 G0. It can be itself, it can be more than 1 G0.
Yeah, that actually now we are taking help of DFT calculation, so maybe you can explain.
Transmission channels can be calculated.
Give now it's kind of experimental observation and whatever I'm telling based on that. So theoretically, whenever you get some data, then I can give better explanation.
Second question is, what is the physical reason behind it happening? When you are putting the HBN, I see that the maximum current is going to the edge, which means it's a leakage current.
Leakage current.
So leakage current is now...
Because whenever you are giving the potential, because you are making the conducting filaments because the set potential actually given. Na? So when this oxygen frequency reaches up to the HBN layer, because HBN is a kind of barrier.
Yes.
So now how to connect with the top contact? So that's why the channel now, this filament, it is now splitted the whole charge across the boundary.
But then there is no control of these
Now,
pockets there.
till now there is no control, but we are trying to control it.
I see. It will be beautiful.
Yeah,
Thank you very much, sir.
welcome.
Okay, that's it.
Thank you, nice talk. I would like to ask about what kind of interactions you expect between this HBM and hafnium oxide. That is my first question. Second question is what kind of band gaps your hafnium oxide is showing actually?
HBN already known, that is around 6 electron volt, and hafnium oxide near about 4. So band gap wise, because it cannot go there because there's a high band gap for HBN. So this is one of the things. Definitely is a good point that you picked up. And regarding the interfacial interaction, so when you did your XPS, we did not find any new phase form. Okay, so that means there is no interaction at least, but we found the strain formation. That means that HBN, whenever it is settled on hafnium oxide surface, it is modified itself, so that some kind of strain is developed.
So the dispersion is uniform or it's a non-uniform dispersion?
It is a uniform distribution definitely, but I cannot control the number of layers. That's the main issue.
Okay, thank you.
So any other questions? Yeah, if not, let's thanks again
Thank you.
Professor Kanjilal for a nice presentation. Thank you. Thank you.